Okay, so let me first take roll. Today is the 5th. Okay, Bartram, Blair, Donnelly is present. Elwell, Levengood is here. Miller, Sheffield, Sullivan, and Tillis. All right. All right, so before I start, let me just say that you had a test coming up as planned next week. What I've decided to do is put that off until the following week because we missed a class last Tuesday. So, and I think that test, if I'm not mistaken, will be based on chapters 1 through 3, but that's a tentative plan. I'll let you know, definitely by next week, I'll let you know exactly what topics will be covered or what chapters will be covered, all right? So just to let you know about that. So we're about to finish chapter 2, which the last part of which deals with naming acids. We started talking about acids and their properties and neutralization reactions, but now we're going to talk about how do we name acids. And let me, before I forget, share my screen so that you guys out there in Zoom will be able to benefit from today's class. Okay, good. So let's talk about how do we name acids. Now, in order for us to do that, we have to understand the different categories of acids. So what I'm going to do here is go to my writing pad here. Let me just do this. Okay, let me get rid of this here. And let me, okay, so first of all, let me just give the 2 main categories of acids that we're going to discuss in terms of naming. One category would be known as binary acids. And then the other category would be oxyacids. All right. And in the case of binary acids, they are made up of 2 elements. Oops. One of which is hydrogen. All right. In the case of oxyacids, as the name suggests, the oxy part, these are acids which contain oxygens. All right. Okay, so what we're going to deal with first are the binary acids. How do we name the binary acids? Well, the thing about binary acids is that they can be formed from a binary molecular compound which contains hydrogen. So I'm just going to use one example. Let's say you have H2S, which is a gas, right? When you add this to water, you're going to get H2S. So you're going to add this to water. You're going to end up with H2S aqueous, right? So this is your gas, and this now, right, this is your gas here, and this now is considered to be an acid, right, because it's now in an aqueous solution. So what you're going to see is that the name that we would give to the gas by itself would be different from the name given to the gas which is now dissolved in water. Now the solution becomes an acidic solution. So how do we name the binary acids? So for binary acids, the name always starts off with hydro, followed by the stem of the name of the other element, and then it ends with ic acid. All right, so hydro, the stem name of, or the stem of the name of the other element, and then ic acid. That's generally how we name binary acids. So in this case here, going back to the H2S example, the name of this compound, before we add it to water, we call this hydrogen sulfide, according to the rules that we learned previously, all right? But when we add it to water, the resulting solution now becomes hydrosulfuric acid. All right? What's your last name? Okay. So as you can see in this example, this here, how I named this, follows the rules that I just mentioned here. Hydro, then sulfur, which is basically the name of the other element, and then it ends with ic acid. So that's one example. Another example would be H2SE. In fact, let me do this. Okay, let me do it here. H2SE, which is a gas, again, which when added to water form H2SE aqueous. So this is called hydrogen selenide. Hydrogen selenide. And this is now called hydroselenic acid. All right. So that's basically how we go about naming acids, binary acids, I should say. We haven't gotten to oxyacids yet, right? So that's how we name binary acids. They always start off with hydro, then the stem of the name of the other element, then ic acid. All right. Okay. As far as oxyacids are concerned, all right, let me just get rid of all of this here. Okay, so as far as oxyacids are concerned, the way we name them can be, there's several ways of approaching it, but I think I prefer this way, right? So when it comes to oxyacids, their names can be derived, based on the name of the, anion from which they're formed. Anion from which they are formed. All right. So let me, I think the best way to go about explaining this is to use some examples, right? And I'm going to use two ions here. This one, which is known as the nitrite ion, and this one, which is known as the nitrate ion, all right? So to convert this to the corresponding acid, because we have one negative charge here, we need to add one hydrogen ion, right? So therefore, the result is an acid whose formula would be this, HNO2. And similarly, in the case of the nitrate ion, to convert this to the acid, we have to add one H plus ion, and we end up with HNO3, right? Now, how do we derive the name of the corresponding acid? Well, according to the rules, and let me see if I can fit that here. If the anion name end with ITE, then the name of the corresponding acid will end with OUS acid. All right. So in this particular case, the name of this ion is called a nitrite ion. So therefore, the name of the corresponding acid is nitrous acid. So the ITE ending here is replaced with OUS acid. All right. Let's erase this here. So that's basically how we deal with that. If the name of the anion ends with ITE, then the name of the corresponding acid ends with OUS acid. So nitrite becomes nitrous. Okay, so that's as far as that is concerned. Now, what about where the name of the anion ends with ATE, right? So I'm going to be a bit lazy here. I'm going to make a few changes to this statement that I made here to explain how we name these acids. So I'm going to replace ITE with ATE. And in this case, the name of the corresponding acid will end with IC acid or IC acid, right? So for example, in this case here, the nitrate ion will be converted to the acid, and the name of this acid would be nitric acid. All right. So just to recap, if the name of the anion, corresponding anion, ends with OUS, then the name of the acid ends with, I'm sorry, if the name of the anion ends with ITE, I'm sorry. If the name of the anion ends with ITE, then the name of the acid, corresponding acid, will end with OUS acid, right? Correspondingly, if the name of the anion ends with ATE, then the name of the corresponding acid ends with IC acid. So nitrate becomes nitric acid, all right? So that's basically what happens when it comes to naming acids based on the anions from which they're formed. If we're talking about oxyacids, remember oxyacids are acids which contain oxygen, right? So just to give you some other examples, let me just clear this here. So this anion is known as sulfurous acid. And in order for us to convert, I'm sorry. I'm messing up today. This is called the sulfide ion. All right. And in order to convert this to the corresponding acid, because you have a -2 charge here, you need to add 2 hydrogen ions to it to form H2SO3. So the name of the corresponding acid would be sulfurous acid. All right. And then in the case of SO4, 2-, again, you have to add 2 H+ ions to get, and by the way, this is called the sulfate ion, before I forget. So when you add 2 H+ to this, you're going to get H2SO4, and the name of this acid would be sulfuric acid. All right. So again, IT becomes OUS acid, and 8 becomes IC acid. All right, just like in the previous example. All right. Any questions so far? Any questions? Any questions? Any questions out there in Zoom? Okay, so can I get rid of this now, or you still need to write this down? Okay, so okay, so this is called the phosphide ion. Okay, so based on what we have just discovered or just covered, how would you convert this to the corresponding acid?
We go ahead and add 300.
Exactly. So the formula becomes H3PO3. So what do you think the name of this acid is? Phosphorus acid. Remember, we changed the IT to OUS acid. Phosphorus, I don't know if I'm spelling this correctly. Phosphorus acid. All right. Okay, and then this here, PO4 3- is called the phosphate ion. And by the way, these ions can be found in the tables, right? Remember, I gave you a list of common ions. You can find these ions there. So this is called the phosphate ion. So again, you need to add 3 H+ to this to get to the formula for the corresponding acid. And the name of this acid is phosphoric acid. And that's basically how that is done, all right? Okay, so that's basically how you name oxyacids. Now, there's one particular acid that I want to talk about, which does not fall into the category of oxyacid or binary acid. And it has this formula, HCN aqueous, all right? Now, this is not a binary acid because obviously it has 3 elements, right? Remember, binary means 2, right? And it is not an oxyacid because it doesn't have an oxygen, right? So this is kind of an outlier in terms of, you know, the category that you, what the hell is this? The category that you put it in. So what the powers of that be, meaning IUPAC, have decided is that we treat the original gas, which makes this acid, as a binary acid in terms of naming only, right? So the name of this particular gas is hydrogen cyanide. And this is something that you do not want to be caught in a room filled with. You will not survive it. Okay, hydrogen cyanide, right? When added to water, it forms this. And according to IUPAC, they have decided that the name of this compound is hydrocyanic acid. So in other words, you're basically treating it as a binary acid for the purposes of naming, right? Even though it's not a binary acid, strictly speaking, all right? So this is kind of separate from what we were discussing earlier. Okay, so that's basically how we name acids, right? Binary acids, oxyacids, and then this unique case of hydrocyanic acid, all right? Okay, so any questions about this? Any questions? Any questions? Now, if I'm not mistaken, this is the very last topic in this chapter. Let me just check and make sure.
So for hydrogen, just add IC at the end. So
For what?
for the binary
For the binary acid,
hydro.
hydro, then the stem, and then IC acid. Yeah, exactly, right. Yeah, so that's basically it for this chapter. So you guys should still have assignment 2, right? All right, so basically now you should be able to complete this because that was the only topic that was left over from last time. So once you complete that, then we can move on to chapter 3. And of course, if you have any questions while you're completing it, please let me know. That's why they pay me the big bucks. What is this thing? Oh. Yes, ma'am. Well, either would do. Yeah, I've seen it expressed in both ways. Mm. Okay, are we finished with that one? I'll give you 4 more minutes because I want to get started with chapter 3 today. Hmm?
What's chapter 3?
Chapter 3 deals with things like stoichiometry, molar mass, empirical, I'm sorry, molecular formula, empirical formula, and all those related stuff. Avogadro's number. A lot of review from your high school or introductory chemistry. Okay, let me get started with chapter 3. Let me get myself together here. Okay, so in chapter 3, we'll be dealing with, as mentioned before, stoichiometry. And stoichiometry is basically that area in chemistry which deals with the quantitative relationships between substances involved in a chemical reaction as products or reactants. But before we get into the actual stoichiometry, of course, we need to review a couple of things that you should have known before. So I'm going to go through this rather quickly. The whole concept of molecular masses and formula masses, very simple concept. The molecular mass is the sum of all the atomic masses of the atoms represented in a molecular formula. And this term is specifically used for molecules. There is a comparative term that is applied to ionic compounds known as formula mass. And that represents the sum of the atomic masses of all the atoms or ions present in a formula unit. Remember that there are no such things as molecules when it comes to ionic compounds. So whenever you're given the formula for an ionic compound, that is basically what we call a formula unit. And it's basically the empirical formula for the compound because it gives you the ratio of the different elements present in that compound in terms of their makeup, ionic makeup. So basically we can do a simple calculation of the formula mass for a compound like ammonium sulfate. Of course, in order for us to answer this question, we need to know what the formula for ammonium sulfate is, which is going to be NH4 2SO4. So basically, to determine the formula mass for this, we have to start off with what's within the parentheses here. We have 2 nitrogen, so we multiply the formula mass of nitrogen by 2, which is 14.01. And by the way, the units for formula mass is AMU, atomic mass unit, right? And then we're going to add that to 2 times 4, which is 8 times 1.008 AMU. And then we're going to add the mass of the sulfur, which is 32.07 AMU. And then we're going to add to that 4 times the molar mass of oxygen, which is 16.00 AMU. And that's it. So let me get my calculator to work this out. 2 times 14.01. And then I'm going to add to that 8 times 1.008. And then I'm going to add 32.07. And then I'm going to add 4 times 16. And according to my calculation, this works out to be equal to 132.15 AMU. So that's basically how that is done. All right. Okay. The next thing I want to talk about is, again, something you should have met before, the concept of the mole and Avogadro's number and the relationship between the two. So the definition of the mole, and by the way, the term mole can apply to literally anything, but in the context of chemistry, we tend to apply the mole concept to very small particles, atoms, molecules, ions, etc., right? So basically, the mole represents the amount of substance that contain as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope. So that's basically what is used as a standard for defining the mole, the number of particles, or I should say specifically the number of carbon atoms present in exactly 12 grams of a carbon-12 isotope, right? And it turns out that that number is a very large number, of course, which is Avogadro's number, 6.02 times 10 to the 23 moles to the minus 1, right? So basically, whatever the substance is, if it has that number of particles present, then we're talking about 1 mole of that particular substance, all right? As I said before, the mole can be applied to literally anything. any items. And just to give an idea as to how large that number is, 1 mole of oranges would weigh about as much as the Earth. All right, so that gives you an idea as to the size of that number. Okay, and very important. So in terms of abbreviation, we do not use uppercase or lowercase m for mole. You either use the mole, M-O-L-E, or in some textbooks, they take off the E and it's M-O-L. So that's, of course, in order to avoid confusion, because uppercase M represents molarity in terms of a unit, and lowercase m represent meters. So in order to avoid confusion, we do not abbreviate the mole unit when you're doing or showing any work involving that. Okay, so just to show you the relationship between, the number of atoms and the mole unit, we're using this reaction as an example. The reaction between carbon and oxygen to form carbon dioxide. And this is chosen because it's a relatively simple equation where you have a 1:1:1 mole ratio between the reactants and products, right? So this would be basically a diagram or a model to represent that reaction. 1 carbon atom reacting with 1 mole of oxygen to form 1 mole of carbon dioxide. So if you were to multiply this by 12 to get 12 carbon atoms, then you'd have to do the same for the others, right? And if you go further to multiply by Avogadro's number, then basically you have to do the same for the others as well. Remember, Avogadro's number represents 1 mole. So basically, we can say, based on the balanced equation here, that 1 mole of carbon dioxide will react with 1 mole of oxygen molecules to form 1 mole of carbon dioxide. So the point that is being made here is that the coefficients that exist for these substances in the equation not only represents what happens at the microscopic level, at the level of molecules or atoms, it also represents the proportions at the molar level, right? So 1 mole of carbon dioxide, based on the equation, we can come to the conclusion that 1 mole of carbon will react with 1 mole of oxygen to form 1 mole of carbon dioxide. And then down here, basically what we're showing you here is the fact that in any chemical reaction, the mass is conserved, because 1 mole of carbon turns out to be equal to 12.011 grams of carbon. 1 mole of oxygen is represented by this mass in grams, and 1 mole of carbon dioxide is this right here. And if you add 12.011 to this here, you're going to get this right here, which is 44.010 grams, right? So basically, there's no matter being created or destroyed as the reaction is, progressing, all right? Okay, so why is this not moving? Okay, so again, just to give you a picture of what we're talking about when it comes to 1 mole, what we're looking at here are 3 different elements: helium in the balloon, sulfur, which is this yellow stuff right here, copper, which is this reddish brown shiny stuff here, and mercury, which is a liquid metal, all right? And these here basically represents 1 mole in each case, right? Now, of course, their masses are going to be different. We're dealing with different elements. So therefore, you wouldn't expect 1 mole of helium to have the same mass as 1 mole of mercury, right? But the key thing you need to remember is what the mole represents. It represents Avogadro's number present in that substance, in that amount of that substance, right? So basically, in the case of helium, we have Avogadro's number of helium atoms. Here we have Avogadro's number of sulfur molecules. Here we have Avogadro's number of copper atoms, and the same is true for the mercury here. So to answer this question, how many atoms of helium are present, and they're asking for each of these, the answer will still be the same in each case. Avogadro's number, 6.02 times 10 to the 23. Okay, then we get to the concept of the molar mass, which we kind of touched on earlier. The molar mass, by definition, is the mass of 1 mole of a substance. And it turns out that the molar mass is numerically equal to the atomic mass if you're dealing with elements, the molecular mass if you're dealing with molecular compounds, or the formula mass if you're dealing with ionic compounds. The difference between them would be the units, right? And I think I have an example here. So the units of molar mass is grams per mole, while the units of atomic mass, as I said before, is AMU. So here's an example. In the case of sodium, the atomic mass of sodium is 22.9 AMU. The molar mass of sodium is 22.99 grams per mole, all right? So please note that the numerical value will be the same, when you compare the atomic mass to the molar mass, but the units will be different. Here's another example. The molecular mass of carbon dioxide is 44.01 AMU, but the molar mass of carbon dioxide is 44.01 grams per mole, all right? So that's basically the relationship. And then we have a formula unit example. In the case of potassium chloride, the molar mass, or I should say, well, in this case, it would be the formula mass of potassium chloride is 74.56 AMU, but the molar mass is 74.56 grams per mole. So that's basically the relationship between the molar mass and the atomic mass, molecular mass, or formula mass, right? It's all about the units pretty much in terms of the difference, but numerically they're the same. Okay, so therefore, based on what we have covered so far, we should be able to solve problems involving conversions from one unit to another as it relates to mole to atoms, let's say, or molecules or ions, and to the molar mass, right? So therefore, we can construct conversion factors which represent relationships between any two of these three values that are equal to each other, right? So one conversion factor could be this, depending on the type of calculation you're trying to achieve. You can use this conversion factor or this, and there are others as well. You could look at the relationship between the number of atoms and the mass of, and the mole of sodium, let's say. So it all depends on the mass of sodium. It all depends on, the type of calculation you're trying to achieve. So therefore, as stated here, whenever you're doing calculations, you may need to use one of these types of conversions, and then you may need to do some follow-up calculations, or you may have to do some preliminary calculations before you use these conversion factors, all right? Now, when it comes to formulas, you can get some information from them based on how they're written, right? Typically, for example, if you're given this formula right here for a compound, right? This molecule, you can interpret this as saying that, okay, for every molecule of this, there are 3 carbon atoms, 8 hydrogen atoms, and 3 oxygen atoms. But because of what I said before, we can actually extend this as far as the molar relationships are concerned. So therefore, we can conclude, based again on this formula, that 1 mole of this compound contains 3 moles of carbon, 8 moles of hydrogen, and 3 moles of oxygen. And this type of recognition of the molar values represented within 1 mole of a particular compound based on the formula can be used in certain calculations, which I'm quite sure you'll see when I give you assignment number 3. Here's another example, same idea. Basically, if you're starting off with 1 mole of ammonium sulfate, then we can conclude that you have 2 moles of ammonium ions, 1 mole of sulfate ions, and you can actually break this down further to look at the respective elements. So in this case here, there are 2 moles of nitrogen, 8 moles of hydrogen, 1 mole of sulfur, and 4 moles of oxygen atoms, right? So basically, we can use the formulas to establish relationships between a mole of a substance and the moles of other elements that make up that particular substance. Okay, so based on what we have covered so far, we can now look at this question, actually several questions in this example. It says determine the mass of a 0.0750 moles sample of sodium, right? So let's start off with that one first. So basically, and again, this is something you should have met before, so I'm just going to go through it rather quickly. So basically, you're given, I'm going to see if I can squeeze this up here. You're given 0.0750 moles of sodium, and you want to convert that to the mass, presumably in grams of sodium, right? So of course, to do that, we have to look at the molar mass of sodium. So we go to the periodic table, and we see that the molar mass of sodium is 22.99 grams of sodium for every 1 mole of sodium, right? So the question now becomes, how do we set this up? Well, we start off with what we're given. We're given 0.0750 moles of sodium, and we have to multiply by the appropriate conversion factor, which represents this relationship. So my question to you at this stage is, what would be placed in the conversion factor as the numerator above and the denominator below?
1 mole on top.
Sure about that? Remember, when you're putting together your conversion factor, you remember you have to set it up such that you're eliminating what you're trying to get rid of in terms of the unit, and you're introducing what you're working towards, right? So what would go up top here? Yeah, the 22.99 grams of the sodium, and down here you're going to have 1 mole of the sodium. So as you can see in this setup, the moles of sodium will cancel out, and then you have to do the number crunching on your calculator, 0.0750 times 22.99, and according to my calculation, this works out to be equal to, rounded off to 366, so that would be 1.72 grams of sodium. And that's how that is done. Any questions?
So I just do mine a tad different. I just do the cross multiplication. And I seem to be getting the same answer. Is that, are we gonna run into an issue with me?
I have no problem with that as long as you include the units. Excuse me. As long as you include the units as a part of the setup. All right. But if I understand what you're saying, yeah, that should give you the same result. My throat. Okay. Let me get rid of this and move on to question or letter B. In this case, they gave you the number, they're asking for the number of moles of sodium, and they gave you the mass. So it's the reverse of what we just did. So they gave you 62.5 grams of sodium, and they're asking for the equivalent in terms of moles of sodium. So we start off with the 62.5 grams of sodium. So again, my question is, what would be in the conversion factor here? What would go up top and what would go below? One mole of sodium will go up top, and the molar mass, which is again 22.99 grams of sodium, will go below. So this goes with that. Let's see what that gives. 62.5 divided by 22.99. And according to my calculation, this works out to be equal to 2.72 moles of sodium. Excuse me. Any questions about this one? Any questions? All right, so let me get rid of this here. And let's look at C. Now, C says you're to calculate the mass of a sample of sodium containing 1.00 times 10 to the 25 sodium atoms. So you're given the number of sodium atoms, and you're asked for the mass in grams of sodium. Okay, so my question to you is, how would you tackle this? Oops, 25. How would you tackle this problem? They gave you the number of atoms, and they're asking for the mass of that collection of atoms. Sodium atoms. I'm sorry? The 22.99 comes into play, but not immediately. Let me just say that since you mentioned that. There's a step that you'd have to do before you get to using the molar mass of sodium. Ouch. So you're saying 1 mole of sodium over Avogadro's number, which is 6.02 times 10 to the 23. Okay, very good. Sodium atoms. So this cancels with that. And then what? What he said, right? 22.99. How would that come into play here? How would you arrange that in this next conversion factor? what would go up top and what would go below? Okay, so 22.99 grams of sodium will go up top and 1 mole of sodium goes below, so that this cancels out with that. So your final answer would be the grams of sodium, which is what the question is asking for. So 1 times 10 to the 25 multiply by, or not multiply, divide by 6.02 and then multiply by 22.99. And according to my calculation, this works out to be equal to 381 grams. Now, it just occurred to me that there's something I probably should have mentioned before that that I neglected to do so. Okay, based on past experience, I've had situations where students have been using their calculators incorrectly when expressing numbers in scientific notation, right? And it turns out that the way you do so on your calculator is dependent on your calculator, right? So it's very important that you guys know how to use your calculators to express numbers in scientific notation. One mistake, for example, that I've noticed students doing is that if they want to enter into their calculator 1 times 10 to the 25, let's say, the first number that we have here, this number that we have here, they will literally enter 1.00 multiplied by 10 raised to the 25, right? The problem with that is that when it comes to more complex calculations, doing it that way can screw you up, right? You'll get the wrong answer. So it's best that you use what is called the exponent function on your calculator. And like I said, in different calculators, you have different ways of expressing it that way. So for example, on my cheap calculator here, which is the Casio FX260 Solar 2, if I were to express 1.00 times 10 to the 25, I would have to press 1, and then there's a key here, which is called the EXP key, right, which stands for exponent. And then I would enter the exponent value, which is in this case is 25, right? And what would appear on my calculator screen is this, 1, and then you see 25 appear like that, right? On my calculator, that's the same thing as 1 times 10 to the 25. Now on your calculator, it is different, all right? And if you need any help with that, I can help you, even though there are some calculators I can't figure out. So that's why I stick to my simple, cheap calculator here, right? Or you may read the book that comes with your calculator when it comes to dealing with that. So I'm just saying that just to let you know that it's very important that you know how to use your calculator when it comes to expressing numbers in scientific notation. Let me see your calculator for a minute. Ouch. So this calculator here is a Texas Instrument TI-30X 2S. And in this calculator here, the way I would use this, let's say I want to express 1.00 times 10 to the 25. Let me clear this first. Okay, so 1.00. And then on your calculator, what I would do is press second function, and then a W key, and then 2.5. So that's that, right? Second function, the yellow key here, and then the WE, where is it? WE key, right? And then you enter the exponent. And that's so it all depends on your calculator. So if you need help with that, you can see me and I'll try to help you. But like I said, I can't make any promises because I've seen some calculators, especially the more, like that one, the graphing calculators, some of them, not all of them, but some of them, I can't figure it out. So, okay, so I just thought I should mention that. All right, so where are we now? So we just did C. So let me clear this. And now we're going to look at D, which says the mass of a single sodium atom. That's interesting. So how do you propose we tackle this one? One atom of sodium. And we need to find the mass in grams. So how would you tackle this one? What would be the first conversion factor you would use? Okay, Avogadro's number. So 1 mole of sodium over 6.02 times 10 to the 23. Very good. Of sodium atoms. Na atoms. All right. So this goes with that, right? What would be the next conversion factor? Remember now, we're trying to get grams. Okay, so in other words, a molar mass, right? Which would be 22.99 grams of sodium over 1 mole of sodium. That goes with that. So let's see what that gives. 22.99, whoops, 22.99 divided by 6.02 times 10 to the 23. Okay, so according to my calculations, this works out to be equal to 3.82. 3.82 times 10 to the minus 23 grams. So that would be the mass of an average sodium atom. All right, any questions about this particular one? Any questions? Any questions? All right, so moving along. Mass percent. What time is it, by the way? Okay. Mass percent composition. Again, this is something that you should have covered from your previous chemistry experience. The definition, there are a couple of ways of defining it. Mathematically speaking, it's basically the percentage of an element compared to the compared to the entire mass of the compound. So one way of expressing it is basically the mass of the particular element for every 100 grams of the compound, or you can use it, you can calculate it this way, the grams of the element divided by the grams of the compound. And that is especially useful if you know what the formula for the compound is, all right? So basically, that's how you determine the percentage by mass of an element. So when you see a question asking about the percent composition, it's basically asking for the elemental makeup percentage-wise for each element present in the particular compound. Okay, so that's the mass percent. So just to give an example, in the case of butane, and they gave you the formula of butane here, which is C4H10. So therefore, to find the mass percent of each element, we have to find the molar mass first. The molar mass of C4H10 would be equal to 4 times 12.01 grams per mole plus 10 times 12.011 grams per mole. So this is what we need to add together. Let me do that now, 4 times. And folks, please do the same calculation with me because I could be making mistakes along the way. And I am willing to accept any correction. So this is 48. This part works out to be equal to 48.04 grams per mole. And we add that to this, which should be 120.11 grams per mole. And then we add that to the 48.04, and that gives you 168 point, how many? Okay, 15 grams per mole, all right? So that's the molar mass of butane. So the next step is to find the percentage of carbon, and therefore we know that the total mass of the carbon per mole is this. So we take 48.04 grams per mole divided by 168.15 grams per mole times 100%. So 48.04 divided by 168.15 and times 100. And according to my calculation, this works out to be equal to 28.57%. And then we do the same thing for the hydrogen, which would be this mass here, which is 120.11 grams per mole again divided by 168.15 grams per mole times 100%. So let's see what that gives. 120.11 divided by 168.15 times 100. And according to my calculation, this works out to be equal to 71.43%. All right. And of course, and I'm quite sure you know this, when you add these two together, you should get 100%, which is the case. 28.57 plus 71.43. So that gives you, in this case, exactly 100%. In some cases, you might get a number slightly off, right? You might get something like 99.99 or something like that. That's fine. That's within the error limits that would be allowed, all right? And you can do this as a check to make sure that you're doing the right thing, because if you work out these percentages and they don't add up to 100%, you know you're doing something wrong, right? So you'd have to go back and check and see where you made your mistake. Yes, sir.
Wouldn't it be in hydrogen, the 10 rows, wouldn't that be like 1.001 per gram?
What are you talking about?
I don't know if I'm just looking at it wrong. Yeah, the 4 carbons
Mm-hmm.
is 12.01,
Mm-hmm.
and then plus 10 times 12.01 again.
Oh, shoot. Thank you. Ah. Big error on my part. So let me correct that right now. Thank you very much. I used the wrong molar mass for the, so this will be wrong. Everything will be wrong, actually. How did I do that? Okay. For hydrogen, the molar mass is actually 1.008. So let me do that right now. 1.008 grams per mole, all right? Okay, so what does this mean? This means that this here works out to be 10.08 grams per mole, right? That means that this here would be incorrect. So what does that give? 48.04 plus 10.08. So this should be 58.12. So 58.12 grams per mole, which means that I need to change a couple of things down here. What do I need to change? I need to change this. I need to change both of this. I need to change this and this. Okay, so for here, this would work out to be equal to 58.12 grams per mole. Okay, so 48.04 divided by 58.12 times 100. So, ooh, is that right?
82.65.
Yeah, 80, well, I got 80, what, times 100, hold on. I got 82.66. 82.66%. And for this one here, I divide 10.08 grams per mole, divided by, again, 58.12 grams per mole. So let's see what that gives. 10.08 divided by 58.12 times 100, and I got 17.34%. Still get 100% here total, but thank you for correcting me on that. So that's basically how that is done. All right. Okay, any questions about this? Any questions? Any questions? How much time do we have left? Okay, 10 minutes. All right. So based on what we have done, you should be able to do, I don't think we need to do these, but I mean, it's up to you if you want to do these. In this case, they're asking for you to calculate to 4 significant figures, the mass percent of each element in ammonium nitrate. The first thing, of course, you need to do in order to answer this question is that you need to figure out what the formula for ammonium nitrate is. And that would be NH4, NO3, right? What they're asking for is to do basically the same thing that we just did for butane, right? So you need to find the molar mass of all this, and then you find the molar mass of the total nitrogen, and then you take the mass of the nitrogen divided by the mass of everything else, and basically you're going to do the same thing for the hydrogen and the oxygen. So I'm going to leave you to do that on your own. And based on the answer here, you should be able to do this question as well. So I'm going to leave you to do that on your own. If you have any questions about this particular problem, or if you want us to discuss it next class, I'm willing to do so. But I want you to try this on your own because I think you should be able to handle that. All right. Okay. Now, in the time that we have left, I want to talk about doing the reverse of what we were just talking about. So what we were talking about before is if you're given a formula or if you're given some data, you should be able to find out the percentage of each element present. But what if, no, actually, you're given a formula, you can find a percentage. What if you're given a percentage and you're asked to find the formulas, right? Which would be the reverse process. Well, the first thing you'd have to do is determine the moles. But before you do that, you need to figure out what the mass of each element is. Now, at this juncture, what you can do is interpret what the percentage values represent. Because remember, the percentage values represent the mass in grams of one particular element per 100 grams of the entire compound. So if we assume 100 grams of the compound, then those percentages would reflect the masses of each element present in the compound. So that would be the first step that you'd have to do if you're given percentage data. The next step is that you'd have to divide the masses for each element by the molar mass to get the moles, right? Which is what we're talking about here. Then we divide right through by the smallest mole value to get the whole number ratio of the moles, right? And that's basically what is described right here. And then once you get those values, then you can go on to figure out what the empirical formula is. So what I'm going to do, and I think this is the very last thing we're going to do, is that we're going to determine the empirical formula based on information provided here. Shoot. Okay, hold on. Let me see if I can. I hope I can copy and paste it onto this. Okay, I'm not sure what's happening here. Oh, okay. Let me try something else. You know what? I'm just going to use Word. Okay, so this is the data that we're given for the percentages of each element present. So let me just show you how to do this problem. So what I'm going to do here is construct a table where at the top, I'm going to have the three elements involved, carbon, hydrogen, and oxygen. And the first row in this table is where I'm going to record the masses. Now remember, we're given percentages here for carbon, hydrogen, and oxygen, right? So what we can assume is that if we have 100 grams of this particular compound, then 76.57 grams of it will be carbon, 76. For hydrogen, the mass would be 6.43 grams, and the mass of the oxygen would be 17.00 grams, right? So that's the first step. We record the masses, which would be the same as the percentages because we're assuming that we're working with 100 grams of the compound. The next step would be to determine the moles of each of them. And by now you should know that in order for you to calculate the moles from the mass, you simply divide the masses by the molar masses of the respective elements, right? So in the case of carbon, it will be 76.52 grams. And the way I'm going to do this is that I'm going to multiply that by 1 mole over 12.01 grams. In the case of hydrogen, that will be 6.43 grams multiplied by 1 mole divided by 1.008 grams. And then in the case of oxygen, I'd multiply 17.00 grams by 1 mole divided by the molar mass of oxygen, which is 16.00 grams. All right. So now we need to do some number crunching in terms of calculating the moles in each case, starting with the carbon, 76.52 divided by 12.01. And according to my calculations, this works out to be equal to 6.371 moles. And then in the case of hydrogen, I'll divide 6.43 divided by 1.008. 6.43 divided by 1.008. And according to my calculation, this works out to be equal to 6.3738, round off to 368. All right. And then in the case of hydrogen, I'll divide 17 by 16. And according to my calculations, this works out to be equal to 1.0, how many sig figs? 4 sig figs, 4 sig figs. So that'll be 1.063 moles, all right? So that's how we calculate the moles. We divide each of the mass values by their respective molar mass. The next step is to find the simplest ratio. And as I said before, we do that by identifying which of these numbers would be the smallest, and then divide everything by that smallest number, right? So obviously, the smallest number is this here, the 1.063 moles. So that means here you're going to have 6.371 moles divided by 1.063 moles, 6.37 moles divided by 1.063 moles. And then this divided by itself will just give you 1, all right? So when we work these out, okay, so 6.371 divided by 6.371 divided by 1.063. Okay, so according to my calculation, this works out to be equal to 5.993. And then for the next one, 6.37 divided by 1.063, that works out to be equal to 5.99, and that is 1, right? Now, when we get a result like this, where we have this number here, which is very close to an integer, we simply, oh, you have a question?
6.38.
All right. I don't think that changes the result much, but you're right. 6.38 divided by 1.063. Oh, so this gives you 6.00. Okay. 6.00. Doesn't change the result much. Anyway, thank you. So whenever you at this juncture get a result like this, where you have a number very close to an integer, all you have to do is just round this up. So this becomes 6, that becomes 6, or we have 1 here. So therefore, the empirical formula for this compound would be C6H6O. And that's it. And that's how you solve a problem like this. Now, there are some other variations of these problems that you can encounter, but we won't get into that right now. We can deal with that next class, all right? So what I'm going to do is I'm going to give you, now for this assignment here, I'm going to, today's what? Today's Tuesday. So I'm going to give you until Thursday to complete it if you have not done so already. That's assignment 2, all right? So you can either turn it into me on Thursday or you can submit it online, and that will take care of that. I have assignment 3 here for you, and based on what we have covered so far, you should be able to do questions 1 and 2, and maybe 3, but I would focus on 1 and 2 for the time being, all right? So what I'm gonna do is leave it right here for you to pick up on your way out, and then we'll continue our discussion on Thursday, all right? Okay, so that's it for today, folks. And enjoy the rest of your day. Ouch.
Yeah.
Yes, sir.